Hello everyone, welcome back to my YouTube channel. Today I'm going to start another interesting topic, the use of expression in Fluent. You know that there are a lot of functions available in Fluent, but they are not always sufficient. So sometimes you need to use UDF to increase the functionality of Fluent. And to use UDF, you need to have some command on programming language such as C++ or C. So there is another way in Fluent that you can use to increase the functionality, that is the use of expression. Although you cannot get all those functionality as of UDF, but still it is very helpful. So most of your problem can be solved using expression. So in this video series, I will go through a couple of examples, starting from very basic to advanced to understand how you can use expression in different scenarios. So let's see what example we are going to see in this video. I will go through 4 different examples to show how you can use expression in Fluent. So starting with very basic example. So I will show you how you can use expression to define variable time step depending upon your different condition. Then in second example, I will show you how you can use expression to define parabolic velocity profile. Normally you use UDF, but same you can do by using expression. Then in example 3, it is a little bit complexer. So I will show you how you can change flow rate based on the temperature of battery cells. So what exactly we will do? So I have shown here this example. You can see there are 2 battery cells, lithium ion battery. So let's say battery cell 1 and battery cells 2. They are generating heat and they are being cooled down by using a cooling fluid. Cooling fluid is entering from here and it is leaving from this side. Battery cells are in direct contact with the cooling fluid. Actually, the cooling fluid is a dielectric fluid. It means battery cells can come in direct contact with this cooling fluid. In this example, we want to control the temperature of this battery cell, let's say at 40 degrees Celsius. So we will write an expression. This expression will check the temperature of this battery cell. Let me bring a pointer. So this expression will check the temperature of this battery cell, let's say after 15 or 20 iteration, and we'll see what is the temperature of this cell. If the temperature of this cell would be higher than the 40 degrees Celsius, so this expression will increase the flow rate. Or if the temperature of the battery cell is lower than the 40 degrees Celsius, so it will increase the flow rate. So it means we will change the flow rate based on the temperature to control the temperature of this battery cell at 40 degrees Celsius. So that's what I meant from the control the flow rate based on the temperature of battery cell. So in example 4, what we will do, so we will manipulate the inlet temperature based on the outlet temperature and the external cooling system. So what does it mean? So again, in this example, so here, for example, the cooling fluid is leaving the system at some temperature, let's say 35 degrees Celsius. And we are saying that the inlet cooling is entering at the constant inlet temperature, but that is not the case in reality. In reality, what happens, the cooling fluid at the outlet leaves the system. Then normally we had some external cooling system. The cooling fluid is cooled down and then it enters at the inlet, and the temperature of the inlet depends on the cooling system what we have and the outlet temperature. So it means cooling inlet temperature will not be constant, but it will be dependent on the outlet temperature as well as on the cooling system. So we will see how we can simulate this one by using expression. So let's start with our first example of the variable time step. It is a one-line expression and pretty much straightforward. And one more thing, in expressions we will use a lot of time if condition. So me tell you, if condition is pretty much straightforward in expression. How does it work? So let me show you here. So that's how normally it works. So you define, or I mean syntax, if condition, if here is condition, then true and false. So that is the syntax. It means if, then you have this small brackets here, you define your condition, and this expression will check the condition. If the condition will true, it will use this value. If the condition is false, so it will use this second value. That's the general syntax of the if condition. So let's go to our first example of the variable timestamp. I have taken same example, so I have already prepared this case, so I'm not going into the geometry and meshing. So we will also see the 3D case of this same example. So what we want to see, so here you can see these are two battery cells, this one and this one, and cooling fluid is entering from here and it is leaving from the other side. And at the start we want, and this one is the transit case, so we want to run a transit simulation, and we want to set a time step at the start of the simulation, very small time step, and we want to increase this time step after some time. So there are two ways. One, you can use adaptive time settings. So adaptive time steps, so here you don't have any control, the software will change the time step by its own. So otherwise you can do it by yourself. So let's say we want to control our time step in such a way that when our time is less than, let's say, 3 seconds, so we want to use a time step of 0.1 second, and when the time is greater than 3 seconds, so we want to use 0.5 second. So we will use the exactly the same condition. So for example, if condition, so what we want to say, we want to say if time is less than 3 seconds, so use 0.1 second, otherwise use 0.5 second. So we can use exactly the same condition, so we can copy paste. For example, let's go over here, and in our case, let's go to the, so to define expression, how you define expression. So here is our time step size. So when you go to the drop down, you can see over here expression, so or expression over here. So we want to create a new expression, so you will go and say new expression. So when you will click new expression, you get this window. So you can do a lot of things in this window, so we will see with the time how we can use. So at top you write the name of your expression, so let's say we call it delta t, and here you write your expression. So let's write our expression completely. So if you always write if in capital, so when you write something and it is already available, so you get this notification. So you can see if is already here. So for if, then small brackets, and then we want to define simulation time. So when you will press time, you can see, so this one is the internal variable, so it recognize expression recognize t, and it will use t as a simulation time. So you can use t less than 3. So here you write, you always write units along with your quantity, so we want to use 3 seconds. So you can also write, for example, like let's say 1 and minute, so you can use whatever unit you like, but we want to keep it in seconds. So let's say when time is less than 3 seconds, then comma 0.1 second, comma So when time is less than 3 seconds, the time step should be 0.1 second. Otherwise, how much it should be? So we said otherwise it should be 0.5 second. So you can see there is no error. It means there is no error. There is no error in our expression. So once you have written this expression, you can click OK. So before clicking OK, you can see there are a lot of things over here. So these are some internal functions. So for example, condition, you can use different condition, and, if, not, or, and so. So we will go through some of these condition in next example. So here are mathematical operation. So absolute, exponential, floor, and a lot of log, min, max, mod, step. So these are all these function. Then reduction. So you, for example, you can calculate area average, and all these function you can utilize. There are trigonometric function, and for example here some variables are available. So we are using time, so time variable is there, and pressure, and density. So a lot of variables are already readily available, so we can use over here some constant values. For example, pi, general gas constant, Avogadro number, Boltzmann, and all these constant. If you have previously defined any expression, so you can use that expression over here. Then report definition. So as I said, we will go few of them in next examples. So we have written our expression, and we can say okay. So it means we will be expecting 0.1 second for the time less than 3 second, and 0.5 second for the time when the simulation time is greater than 3 second. Okay, so let's run this simulation. So delta t is here. Let's run this simulation for 50 time steps and 20 iterations. So I'm not going into these settings, but one thing, we want to plot the delta t so that we can see. So for that, here in report definition, we already have delta t, so we can create a plot for this. I have already created. So if you go over here, report plot, so I have created plot for delta t. It means it will plot the delta t for each time step. So click OK. So let's initialize our simulation and run. So initialize and calculate. Okay, simulation is running, so let's wait a little bit. It has started. So over here, so you can see right now the time step is 0.1 second, and here you can see flow time. So our simulation time at the moment 1 second, 1.2, and you will see till 3 second the time step will remain 0.1, and it is increasing to, so just let's see. So it means at 3 second it will jump to the 0.5, and now you can see it is at 0.5 second. So it means you can define whatever condition in here in time steps, and that you can use. So you can write a UDF for this time step, but I think with the use of if you can use expression, you don't need UDF to define different time step. This conclude our example 1, where we have seen how we can use the expression to define delta t. In second example, we want to define a parabolic velocity profile. So the formula for parabolic velocity profile is something like that. Velocity profile is equal to maximum velocity 1 minus r over r square. So that is the formula for the parabolic velocity profile, where u max is the maximum velocity, 1 minus r is the distance from the center. So any distance, for example r is the variable that is the distance from the central point, and capital R is the radius of our pipe. So it means we need to define u maximum, small r and capital R. So let's go to our Fluent and define our velocity profile for the example 2. So it is little bit complexer but not so much, and we can see how we can do that. So let me close this one. Okay, and for this parabolic velocity profile, I have taken a simple pipe, and here is our inlet, here is our outlet, and we want to define a parabolic velocity profile over here. So as I mentioned, we need three constant: u maximum, small r and capital R. So let's go and define over here. So for velocity profile, so that we define velocity profile, we would define velocity profile at the inlet. So if I will go over here, and here at the velocity profile, I can write expression over here. If I go, so let's call it velocity profile. So velocity profile is u max into 1 minus, let's call it radius over radius over radius square. Okay, so this one is the expression for our velocity profile, but you can see this box is red. And why it is red? It is saying u max is not defined, although radius and this radius is also not defined, so that's why we are getting this error. So we will leave it as it is, and we will define our these constant, but we can click OK. Let's say click OK, and our profile is already here, so expression is already here. Let's say u profile is not defined. Okay, that we know, and close this one. So when we define any expression, so you get that expression over here, and you can see this one is invalid at the moment. So there in this if I open this one, so you can see in this expression all these variables are undefined, so we have to define these variables. So those variable we can directly define over here. So new expression, let's say new, and what we need to define, we need to define u max, and let's say 0.2 meter per second. Oh, we always define every quantity along with their units. So u max is 0.2 meter per second. Say okay, and so we have defined u max, but we need to define small radius and bigger radius. So first let's say radius. So the radius of this pipe, I already know it is 10 millimeter. So it is 10 millimeter, and click OK. Now we have defined capital radius, small u max, and now we need to define small radius. And small radius, so it means that is not a single value, but that is changing, and it depends on the value of x and y, or the coordinate at the center is 0 and 0. So how we can define the radius? So we will use the equation of the radius, and that you already know, I guess. Equation of the radius is x square plus y square and sqrt. So square root of x square plus y square. That's how you define the radius of any point, or the distance from the center. Distance from the center of any point by using their coordinates. So x square plus y square square root. So this one is their small radius, so we will say okay. As you will click OK, so you can see our U profile is now valid, so there is no error. So now we have defined everything. If you go at the inlet velocity, so it has been we need to select again U profile, apply OK and close. So now let's run this simulation and then plot this velocity profile and see what we get. So number of iteration, let's just run 10 iteration. Initialize and OK. So I have simulated for 10 iteration. Let's see our velocity profile. So for that, let's go to the graphic, contours, velocity. Okay, let's plot for all of them. And here. So here you can see velocity is changing. So at the center we have maximum velocity and towards the wall it is decreasing. So that's how we had defined our velocity. So that's how the parabolic velocity profile. So here is 0 increasing maximum and then it is going again back to the 0. So that's how you can use expression to define your parabolic velocity profile. So just one clarification for this small radius, actually here this one is called the equation of the circle, or it is simply Pythagoras theorem is also based on the same equation. So for example, here are origin and one point is here now, so you will take, so here is the x distance and here it is the y distance. So x square plus y square is the distance of that point from the center. That's how we have defined this radius. So it will take all those points and it will define at each point, it will define the velocity based on this formula U profile. So a small exercise for you may be just to test what you have learned. So in this example, our origin or our pipe was at the origin, exactly at the center point, or the center point was 0 and 0. So let's say your center of the point is not 0 and 0 at some other coordinate, I don't know, 20 and 30. So in that case, how you would define your radius or how you would define your velocity profile? Just take any origin other than 0 and 0. So any coordinate at this center, 20, 30, 50, 50, whatever, and then write your expression and leave it in the comment below or check by yourself. So, and I will see if it is correct or not. This conclude our example number 2. So where we have seen how we can use expression to define our parabolic velocity profile. So you can see we don't need any UDF and we don't need to go through any programming language C++, C or anything else with simple mathematical expression. We can define these kind of profile, or we can do a lot more things. In the next video, I will go through our example 3, where we will see how we can control our flow rate based on the temperature of the battery cell. Thank you for watching and see you in the next video. And one more thing, if you like this content, so don't forget to like and subscribe to my channel. It will help me to make more videos and to grow. Let's continue with the third example of the expression. As I mentioned earlier, in this example, we want to control the flow rate based on the temperature. So it means this expression will check the temperature of this battery cell. If it will be higher than or lower than the desired value or the target value, it will adjust the flow rate accordingly. So it is a little bit complexer problem. So for simpler expression, you can watch initial two examples. I will provide the link in the comment below or in the description. So let's continue with the expression. First thing first, whenever you're writing an expression, always start by writing a rough algorithm in a text file or on a notepad. It will give you an idea how your expression will be constructed and how you are going to implement in the Fluent. Let's write our expression over here by writing our requirement. As I said, we want to control the temperature of the battery cell. Let's call it target temperature. So we need target temperature, let's say 40°C. Then we have our initial flow rate. So let's call it flow initial. I would start with 2 gram per second. Okay. Then what we want to do actually, so after every 10 iteration, the system will check the temperature of this one, will compare if the temperature is lower than 40°C, then it will decrease the flow rate so that the temperature of the battery cell will increase. Or if the temperature of battery cell would be higher, it will increase the flow rate to further cool it down. So it means that's why we have our target temperature, we have our flow rate. We want it to check the temperature after every 10 iteration. So for that we need if statement. So what we want to do, so for first initial 10 iteration, we don't want to change the flow rate. So it means initially we will give 2 gram per second. After 10 iteration, it will check and change or not depending upon the condition. So for iteration less than 10, flow rate, if the iteration would be less than 10, so the flow rate should not change. So it means our flow rate should be initial, flow initial, right? Or after 10 iteration, the flow rate should change. So let's call it mflow modified. So it means for first 10 iteration, the flow rate will not change. It will use 2 gram per second. And after 10 iteration, it will be modified. Now we need to see how this flow rate should be modified. So these are all expression that we will be adding in the Fluent one by one. We could add side by side or we can do it later. Okay, let's add all these side by side so that you know what we are doing. Okay, graphical window, yes. So here are simulation case. So we have two battery cells, fluid is entering from here and it is leaving on this side. So on both of these battery cell, I have provided heat source that you can also see from here how much heat is provided. So heat is this much watt per cubic meter. So because we have to provide heat in cubic per meter, so it is approximately 2 or 3 watt per battery cell. I don't know, I have to check, but you can get by dividing by its volume. So if you will multiply this number with its volume, so you will get in watt. How you do that? So maybe you are already aware. So for that, you always go to the cell zone, solid. You go to the cell, and when you check this heat source, you would see over here heat source, and here is your heat source. So here you have used expression. So that's it. So same condition have been applied on the cell 2. So now we want to apply these conditions. So let's start with the t target by defining our name expression. So first we want to have our t target. I think we can use capital. Okay, t target, yes, 40°C, or you can provide in Kelvin, 3.313.15 Kelvin. So it is 40 degrees Celsius. So if you refresh, you will also get the current value. So we have defined our target flow rate, target temperature. Then we need to define our flow initial, that we will be giving 2 gram per second, right? So whatever unit you can provide, if you would say kg per second, so you have to give 0.002, so it is converting into SI units, 2 gram per second. Then what was our third condition? If iteration less than 10, so we can simply copy this one. So okay, the formatting, so flow initial, okay, and let's call flow in. So we are saying whatever flow it is going in. So if iteration is less than 10, so if this condition is true, use flow initial. If it is false, then use this one. So our entire effort would be focused to define this mflow modified. And you are seeing this one is red, it means there is an error, and you can see mflow modified is not defined. So that's why you're getting this error. So it is fine. So we will define this one mflow modified. So let's call it okay. So what we want to do, as I said, we want to check the temperature of this battery cell. So it means during simulation, we have to extract the temperature of this battery cell, average temperature. How can we do that? We can do this by report definition. We can do it directly, but I would prefer do it in report definition because it will be much easier. I have already done over here, but let me delete this one. So how you do report definition? For that, I have detailed video for that about report definition. You can check it later. I will provide the link in the description. But anyway, how you would do that? You will go to the report definition, new, and volume report, and you need to define volume average temperature. Volume average, when you will go over here, you can give it a name. I'm not going to define, I will just show you. Then you will say okay, volume average already here, and then you will select temperature, and we want to select for cell 2. I'm not going to do that. Why? Because I have already here, so I just call it current temperature. So I have just given it a name, current temperature, volume average, temperature total and static is same, and it is for cell 2 because that's our target cell that we want to compare with the 40 degrees Celsius. And here I have activated report plot. It means we will also plot this temperature during the simulation over here. So we have defined current temperature that we want to compare with the target value. The other thing, we also want to check the current flow rate. At every iteration, we want to extract flow rate because flow rate would be changing, and we want to see what is the current flow rate at the current iteration. How you can do that? You can also do that with the report definition. I have already done that, but anyway, how you can do that? You will go to the new flux report, and you will say mass flow rate. So you can call it current flow or whatever name you would like. So current flow. Okay, I'm just defining again for you. We don't want to report, plot or file, and we need a flow rate at outlet temperature, and you will say okay. And we have this current flow over here. So both are same, this one and this one, because I have already defined. So but I did it again to show you how you can do that. Sorry, yes, it should be at inlet here. I have just made a small mistake. I said at the outlet, but it should be at the inlet. For that we can do something else. So we can take the sum just to check the net flow at every iteration, just as a fun, or to see the convergence of the flow rate, and we want to plot this one. Okay, so we have defined our current temperature, current flow rate. This report definition, you can call these things also in named expression. So Coming back now, what we need to define, as I said, we need to define this mflow modified. So how we would do that? So we have two conditions that we need to check. First condition is for the iteration. We don't want to change every iteration, but at every 10th iteration. Secondly, we want to check the temperature if it is lower than or higher than or equal to current temperature. So first let's apply the condition for the iteration. How you would do that? That again we can do with the if condition, and there is one function which is called mod. Mod is like so let me write, then I will tell you. Mod iteration is the internal variable, so it is the current iteration. So iteration comma 10. So what this function will do, so it will take the iteration, it will divide it by 10, and it will check if the residual is 0. So it means if it will be 20, so residual will be 0. So if condition will be satisfied. If iteration will be 25, the residual will be 5. So condition will not be satisfied. So that's how mode will work. So it's just the division and check the residual if it is 0 or not. For mflow modified, we want to use if mod iteration comma divided by 10 is equal to 0. If it satisfy, then you can use the, let's call it, because we need a few things, so let's give it an error, or let's call it x. We can change it later, x. So if it satisfy, then change the flow rate. What it should be, that we will see. And this one is equivalent to this one, right? X, if this condition is satisfied, it should be x, otherwise whatever current flow rate that we have defined in our Fluent. Otherwise use the mflow current. So mflow current. So let's copy this one and paste in a new one. So now we need to go to the name expression, and we will copy paste this entire thing over here. And what should be the name of this one? It should be mflow modified. Okay, it is giving an error with the x. Why? Because x is also an internal variable. So let's call it mflow conditional. So again, it is showing mflow conditional is not defined. That we will define in next step. And what is mflow current? Mflow current is the report definition what we have defined over here. So you can see how you can do that. If you just simply write, so it will show you mflow and it is current like that. Otherwise you can also go over here, and all those report definition are available on the right side. Report definition and this mode function, these are also available over here. So these function are available. So there are a lot of functions, so constant values, expressions. So we are using where is mode? Should be here. Yeah, here is mode, square root, and a lot of function are there. So we have defined so mflow conditional. And now we need to define mflow conditional. Why I did like that? Because one condition we have defined, but still we did not say how it should behave with the temperature. So that's why it is going into the steps. So let's say okay. So again it is showing invalid. That's okay. Mflow modified, and okay, mflow modified is not defined. Mflow modified, yes, it is okay. Now the third step. The next one we want to say about the temperature. What was our condition for temperature? If, let's call it absolute, while first let me write T underscore target minus current temperature. So we want to take absolute value of the difference of these two. If the difference of these two is greater than whatever number you can say, we can call it 1 Kelvin, zero point 0.5 Kelvin. So it depends. If you say 1 Kelvin, we'll find out the temperature between 39 to 41, or you can say 0.5. So let me put it 0.5. If the difference of absolute difference of these two is greater than 0.5 Kelvin, then it should change the flow rate. So let's call it M flow adjusted. So we are giving another name because we need to define how it should be like that. If it is less than 0.5, then it should give the M flow current. And this one is okay here. What we had, M flow conditional. Let me make it little smaller. It is too large. So what is RM conditional? RM conditional, it is checking another condition for the temperature. If it is greater than 0.5, it will adjust the flow rate. If it is not, then it will use this one. You can do one thing. You can put this entire statement at this place. In that case, this statement will be too long. It will work, but sometime it becomes difficult to find an error. That's why I'm doing it separately. But you can also do that. You can just copy and paste this one over here like that. So you can see there are a lot of things. So I don't do that. It makes life easier like that. Now, okay, now we have defined this. We have defined both of these conditions. Now we need to see how this flow rate should be adjusted. So how it should adjust? M flow adjusted, it should be equal to the M flow current plus M flow current time any factor. So we can define this factor. It is not that important. So what we are doing here? So we are saying the M flow adjusted. So how this flow should adjust? So it means it should take a current flow and not equal plus. It should take a current flow, and if these two conditions satisfy, if the iteration is equal to the multiple of 10 or the difference is greater than 0.5, then it should take the current flow rate and it should add some value in this current flow rate, which should change for the current flow rate by some factor. So that is our adjusted flow rate. Now we have, so now we just need to define this factor. This factor you can define in different ways, but the easiest way that I find, so that this factor should change according to the temperature. So if the difference is big, the factor should be bigger. If the difference is small, the factor should be smaller. So you can define in different ways. So there is one way how you can do that I have done over here. So it is something like that, a factor of 5. So here, so what I am doing, so it is taking a current temperature that we are getting through report definition in Fluent here, that we have defined current temperature over here, or the current temperature of the battery cell. So what is the factor? Current temperature minus target temperature. So it is checking how far this temperature is. So current minus target divided by target. So it is checking in term of percentage, or actually in term of fraction. So it is checking how far this current temperature is from the target temperature. So, and I'm just multiplying with another factor of 5 because that just give a reasonable change in the flow rate. So you can adjust this one. But the beauty of this factor is that for example here, if the current temperature is higher, so it means this factor would be positive. So that's what exactly we wanted to have. If the current temperature is higher, we want to increase the flow rate. So that's exactly what happened. So current minus target, this factor will be positive. So it means this entire expression will be positive and the flow rate will increase. Or other way around, if the current temperature is less, so our target is 40 and current temperature is 35, so it means it will be negative, or the system is extra cool down, so we want to reduce the flow rate, so it will automatically subtract from this one. So it means this factor works really well, so it can work in both ways, positive and negative. So you can do it separately, or you can just simply write over here, so it's up to you. Now let's go back and let's copy this one. So we need to define our amp flow conditional. Let's go back. So we need to define amp flow conditional. So let's say new. Let's write our expression over here, and here we have amp flow underscore conditional, amp flow conditional. So if absolute t target minus t current, so we have taken absolute, so here the order doesn't matter. It is saying there is some error. So let me check what error do we have. Syntax error. T underscore target. So this one we already have. Okay, let's write from start. I don't know what is missing, but okay. Absolute T underscore target minus what we had defined, current temperature is okay, we need here and here one bracket greater than 0.5 Kelvin. Then we want to use amp flow adjusted, otherwise amp flow current. Yes, now we don't have any syntax error. Yes, this one should have been in the brackets. So now if target minus current is greater than 0.5, we should have amp flow adjusted, otherwise the current flow rate should be used. So let's say okay, again amp flow adjusted is not defined. Yes, that's fine. Okay, now we have to define last one, amp flow adjusted. Say okay. Now new, and here we want to define amp flow underscore adjusted, and here we have already defined, so not here, from here I can simply copy paste this one over here, target temperature, but T underscore target, and again here T underscore target. Okay, so now amp flow current, so current flow rate plus current flow rate into that vector, and we can say okay. Now you see we have defined everything, so now everything has been defined. So now what we need to do, just we need to set at the inlet amp flow in, that's where we had started. So let me pull that back. So amp flow in, so that was the amp flow underscore in, so that's how we had started. So it means it is the expression that we have to put it at the inlet. So let's go back and say, let's go our inlet, edit, or just go over here, mass flow rate. So I have already converted into the mass flow rate, and in drop down you can see all those mass flow rate, and here just select the correct one, amp flow in, because if you will select something else, so all these expression will not work. So just say amp flow in and apply, and okay. So again it will go in this order. We have defined target flow rate, sorry, target temperature, we have defined initial flow rate, and we said okay, our boundary condition is this one, amp flow in. So what it will do, amp flow in, it will go and check iteration is less than 10. So if when the iteration is less than 10, it will use initial flow rate, which is 2 gram per second. When it will be greater than 10, it will use amp flow modified. What is amp flow modified? That we have defined over here. Amp flow modified, for that we want to apply two conditions. One is for iteration, other one is for temperature. So let's do it one by one. if mod iteration 10 is equal to 0. So if the residual of this one is 0, it means this condition will be satisfied. If this condition satisfy, then it use mflow conditional. Mflow conditional that we have defined in next step. If this condition doesn't satisfy, so it will use mflow current. Mflow current is whatever flow rate was in the previous iteration, so that will continue. And this mflow current we have extracted through report definition. So now we have to define mflow conditional. Mflow conditional is over here. So here we are defining mflow conditional, and here we need another condition because we wanted to have two conditions. One is for iteration, other one is for temperature. Now, if absolute T target minus current temperature, so it will check the difference of these two, target minus current, and it will take the absolute. So absolute, so it means it will disregard this sign. So if the absolute difference is greater than 0.5, then it will change the flow rate. If it will be less than 0.5, so it will continue whatever the flow rate was in the previous iteration. So it depends, this number, it depends on your requirement. Now we need to define this mflow adjusted. So it is straightforward mflow adjusted. It should be current flow rate plus current flow rate into some factor. This factor you can use hard factor. You can say, let's say 10%, 20%, 30%. But that's not a good idea, because let's say if you say 20%, it means the change will always be 20% regardless of the difference between these two. So we need some dynamic factor that could change accordingly as the difference between these two. And also this sign should also change, because if you use hard factor 20%, then it means if you also need to change the sign for uh, both condition if the temperature is higher or lower. So that's why we have copy this condition with this expression. So we say set current temperature minus target temperature divided by target temperature. Oh, we have defined our all of expression in the Fluent, and now we're ready to run our simulation. Right click. Okay, let's go to the run calculation. Here I have defined maximum iteration of 500, and you will see that the flow rate will change as the simulation will progress. Right click and run. It will take some time to run the simulation, so I will stop in between, or I will fast forward, and in between I will give some comments and see what is happening. A couple of iterations have already been finished. So here you can see the flow rate is changing after every 10th iteration. So after 10th iteration, flow rate has increased, after 20 further, and after 30 further. It is happening because of the temperature. So you can see initially in first 10 iteration, temperature went up to 45 degrees Celsius. So temperature was quite high. It has changed the flow rate, and we had seen after 10 iteration flow rate had increased. So after 10 iteration it has reduced up to 44 degrees Celsius, and it is keep on decreasing. So it is going forward. So as soon as the simulation will finish, I will show you the end result. And one more thing in between I can show you. So here is the residual. It is behaving like a quasi-transit simulation. So you can see the residual is going down, and after 10th iteration, when the flow rate has changed, it has increased once again. So it is going up and down, up and down. Let's stop here and see the simulation results at the end of the run. The simulation has almost finished, and here you can see the flow rate had increased up to 6.5 gram per second, then it decreased once again. It happened because initially I had given the target temperature of 35 degrees Celsius and it was increasing. Then I changed it again to, and the current temperature went below 40. It was 39 or something, so I changed the target temperature to 40 degrees Celsius. So now the current temperature is increasing again and the flow rate is decreasing. Here the residual has almost uh, reached, so we have reached the end of the simulation and we have fully converged solution. And here is our temperature. So first, as I mentioned, it went below 40 degrees Celsius, almost 39, where I changed the target temperature to 40 and it increased once again up to 40 degrees Celsius by increasing the flow rate. Now let's look at our end results. So I have plotted the temperature. Here you can see the temperature of these two battery cells and we can see the temperature in report plot. So let's go to this report and volume integral, volume average, we want to see the temperature. Let's okay, volume average temperature and compute. And here you can see the cell 2 temperature. Average temperature is 39.5. So I had used a temperature condition of 0 0.5 Kelvin, so it is in between 40 plus minus zero point 0.5, so it is in between 39.5 to 40.5. So that's how you can use expression to manipulate the flow rate to achieve the required temperature. So that's it for today. In next video we will look at our fourth example where we want to change the inlet flow rate based on the outlet temperature, and we will write the series of expression like that for that example number 4. If you like the content, don't forget to like and subscribe my channel. Let's continue with our series expression in Fluent. So today we will continue with our example number 4. As I mentioned earlier, in this example, we will check the outlet temperature, then it will go to the heat exchanger and it will lose some heat based on the cooling capacity of this heat exchanger, and then this fluid will enter at the inlet. In this example, there are 10 modules in parallel. I have shown only 2 modules. We will simulate only one module because all these are in parallel, so we are assuming that each module is getting same flow rate and the condition of the temperature in each module will be similar. And everything what we mentioned, we will achieve this through expressions. So here are some parameters that we need to consider. So these are lithium ion battery and each cell is generating 5 watt heat. And as I said, we have 10 modules, so these are 10 modules and they are in parallelly connected. Mass flow per module is 4 gram, so through each module 4 gram is passing, so it means in 10 module it will be 10 into 4, 40 gram per second would be passing through the total system. And the cooling capacity of our heat exchanger is 200 watt. It means whatever fluid will enter at the heat exchanger, 200 watt heat will be removed and rest will remain with the fluid and it will go to the inlet of these modules. And the initial temperature is 20 degree Celsius. So we have another condition that the minimum temperature of the fluid will be 20 degrees Celsius. So for example, if fluid is coming over here at 22 degrees Celsius and after losing 200 watt, it might go maybe 15, but we will pose a condition that the minimum temperature it could go 20 degrees Celsius. Now let's start with our expressions. And actually before going into the expression, just let me show you the geometry. So that's how our geometry look like. As I said, we will be simulating only one module. Even that module will be in symmetry. So I'm not going to show you the geometry. Maybe I will show you this complete simulation in another video, but here I will just show you the geometry that I have already prepared. So I have cut this geometry from center and also from here. So it means we will be simulating only this much portion, 1/4. We will be simulating this much. And as I said over here, through each module 4 gram per second flow rate would be flowing. So it means through 1/4 we will have flow rate of 1 gram per second. So now let's continue with our expression. So we will do in parallel or side by side. So we will write some expression over here on our slide. Then we will put those expression into the Fluent. Let me bring this one over here so that we don't need to go back and forth again and again. So first what we will do, we will define our flow rate. So we will say our flow rate is 4 gram per second. So let's say mass flow. So all these things what I am writing here now, we will do, or we will put all these things into our expression. So flow rate will be through each module will be 4 gram per second. So through 1/4 of the portion will be 1 gram per second. And then what we will define, the initial inlet temperature would be 20 degrees Celsius. And what else do we need? Yes, cooling power. And as I mentioned above, cooling power is 200 watt. What else? Yes. So one condition was the temperature cannot go below 20 degrees Celsius, and the other condition, the temperature would start changing after some time, let's say after 50 seconds. So why is this so? Because for example, fluid is coming from here, so it will take some time to reach at the inlet. So I have just taken random time, so you can choose based on your requirement. So I'm just saying that it will take 50 seconds to reach over here. So we will pose another condition that the inlet temperature would be affected by the outlet temperature after 50 seconds. Okay, so let's put all these three condition in there. Actually, I have done all these things over here, but let me pull another new Fluent, and then I will show you from scratch how we will do that. Here is a Fluent case. As I mentioned earlier, we will simulate only 1/4 of the geometry. So here is inlet, these are two battery cell, and here is outlet. Let's continue with our different definitions. So everything we will define over here in the named expression. Few things we can define directly, but we will do everything over here. So first let's define our heat source. We will call whatever name you like, can give it to that heat source. So I'm just giving this number 500,000 watt per meter cube. W should be capital. Okay, so yes, watt per meter cube. Heat source 500,000 watt per meter cube. I have taken this number. I think it is not 5 watt, but what you can do, you will take 5 watt and you will divide it by the volume of the battery cell. That's how you will get the heat source in watt per meter cube. But that's not important. Okay, we have defined this one. Let's take this source to the cell zone. So this one is our battery cell, cell 1. Yes, I have activated heat source. So you will go to heat source. One source you can define constant over here, but we have defined, you can see heat source is appearing over here. So it is smart enough to recognize what parameter should appear at which position. It knows heat generation is in watt per meter cube and it is appearing over here. Heat source, okay, apply and close. We can do same over here in cell 2, but we can also do copy paste. So we will do copy from cell zone, cell 1 to cell 2 copy. So we don't need to repeat everything, just to copy, and if you can check, it had copied everything over here. Similarly, now we will define the mass flow. So we will call it mass flow, and let's do it 1 gram per second mass flow. Okay, and that we will take to our inlet, and it is already mass flow and mass flow that we just defined. We can put it constant 1, it was already 1 here, but we want to keep it to mass flow so that if we want to change outside, it will change automatically. Mass flow, and you can see I have already converted inlet into mass flow boundary condition. Normally you get in velocity, but you know that you can change easily by right click. So you can type. So here are different types of the boundary conditions. What was the next one? Next one was the initial temperature. So let's call it T initial 20 degrees. So let's keep it in Kelvin. That is easier because it deals in SI units. So 20 degree is 293.15 Kelvin. I think you can also do like that 20 degree, and it will convert it into Kelvin by itself. Okay, doesn't recognize small c, capital yes. So it will convert it into Kelvin. We have defined all these three parameters: mass flow, T initial, and cooling power. Now, what was our first condition? As I said, we want to change the inlet temperature after 50 seconds. It means for that we need an if condition. So if time, okay, first let me write this one, then we can talk about this thing. 50 second, then use T initial, otherwise let's call it T conditional. So what we are saying, if time is less than 50 second, in Fluent T is the internal variable Fluent recognize as a flow time. So it will check time at after every time step and will compare with this 50 second. If this condition will be true, it will use this one. If this condition is false, it will use this one. T initial we have already defined 20 degree. So that's how we will define this one. So let's put it over there. New, what we can call this one. We can copy paste our entire statement. If T is less than 50 second, T initial, otherwise T conditional. It is giving an error that T conditional is not defined. Yes, okay. And we know that. So let's call it T in. Okay. That we will take into the that we will define into our boundary condition. But first we need to define T conditional. And we will say okay, and you can see it is saying T in is invalid because T conditional is undefined. We can now define T conditional. Why I am calling it T conditional? First give me a second. Once I will define, then you can see why I am calling it T conditional. So what I said initially, that the temperature cannot go below 20 degree Celsius. Yes. So let's call it if inlet temperature less than T initial, then use T initial, otherwise inlet temperature. So what is our T conditional? Our T conditional is this definition. So what we are saying whatever inlet temperature is, if it is less than T initial. What is T initial? 20 degree Celsius. Then use T initial, otherwise use some other temperature that we have to define. So there was another condition which I spoke earlier, that inlet temperature cannot go below 20 degree Celsius. So exactly that's what I have mentioned over here. If inlet temperature less than 20 degrees Celsius, use 20 degree. If it is greater than 20 degrees Celsius, then use whatever that temperature is. So let's put this statement into our Fluent, and we can. So this one was our T conditional. T. Okay, the statement is correct. Now the last step, we need to define inlet temperature. Now, how can we define inlet temperature? That's pretty much straightforward. So because here fluid is coming over here, it is losing some heat and it is leaving out from the heat exchanger. So you can use simple formula, that is mCp delta T. M is the mass flow rate, Cp is the heat capacity of that fluid, and delta T is the temperature difference at the inlet and outlet. That is the simplest equation that you can use. So cooling power is mCp, m into Cp into delta T. So we need delta T, and delta T, you know that delta T is equal to T outlet minus T, or it is just the difference between these two. So you can take care of those signs. Oh, okay. So cooling power, we already have 200 watt. And mass flow rate, we already know. Cp, that we already know because we have defined that fluid. So heat capacity of the fluid is already known. Delta T, so delta T is the outlet and inlet. So we know one temperature, whatever temperature is coming over here, whatever temperature, so through simulation we knew this temperature, so we know everything, and from this equation we can calculate the temperature on the other side. So you can separate the inlet or this temperature from this equation. I think this one is pretty much straightforward, you can do that. So I am just writing directly the final equation, but we can talk about that equation. So what is that equation? That's here. So let's call it inlet temperature. And so here is cooling power, so everything mCp will come into denominator. So you can see mCp has come into the denominator. Here is cooling power, and then delta T, so it is just we have separated inlet and outlet. So mCp, m sorry q over mCp and outlet temperature. So that's how. So here is the delta T. So you can take from here what, okay, so from this equation, m and Cp will go here in denominator. T outlet minus T inlet will remain here. So you, what will happen, T inlet will come over here, and this entire factor is over here. So that's what exactly happened over here. We can take this entire, okay, and the other thing here, why did I use 10 into 4 into mass flow rate? So mass flow rate is only 1 gram per second, and this 200 watt cooling power is for entire system. So it means we need to consider the mass flow rate for all modules. So 1 gram or the mass flow rate, what is defined over here, it is only for 1/4 of single module, that is 1 gram. So that's 4 is over here because of that symmetry, because we are using 1/4, so that's why we are multiplying with 4, and 10 is because of 10 module. So it means this one is the total mass flow rate. Now we can copy paste this one over here, and we can go to Fluent, and we can say what was the name, because we need to use same name, inlet temperature. So we can say cooling power is not defined, so we okay, heat source is something else, so we also need to define cooling power in watt. I will come back over on this one later. Okay, cooling power is 5 watt. Inlet temperature, I will come back to the cooling power in a minute. It is double W. Okay, there is just a small error. Okay, first of all, outlet temperature. So it recognize outlet temperature. How? Because I have already defined outlet temperature into report definition. Outlet temperature over here. So if you go in outlet temperature, and you can see I have already defined outlet temperature, mass, weighted average, and temperature at the outlet. So outlet temperature we are already getting from simulation. So you can use directly. Cooling power I have just defined over here, 5 watt. Actually it should not be, so sorry, 200 watts, so that is over here. Actually we had cooling power already. Before that, just a small mistake, so let me rectify that one. Actually cooling power is the cooling power of the system, 200 watt. It is not the heat generation. I was mixing cooling power with the heat generation. I have defined cooling power 200 watt. Okay, I did not define before. Okay, doesn't matter. Let's go back. Outlet temperature, cooling power divided by mass flow rate into specific heat, and everything has been subtracted from the outlet temperature. So that's how our inlet temperature is. So you see, as soon as I have written this expression, everything has come into place. So we can click OK. So we have defined all of our expression. Now the question is what we need to take into our boundary condition. Into our boundary condition we need to take this one, because that's how it will go. It is saying if time is less than 20 whatever 50 second, then use initial and then t conditional. Then it will check, it will go and check what is t conditional. So it will go over here into the t conditional. It will come over here and check t conditional. In t conditional it will find another one inlet temperature, and then for that it will come over here. So it means we, in our boundary condition, we need to define over here so that it can go to the lower step or lower levels. Now we will go to our boundary condition, and in thermal you can see all those temperature would be there because all these are temperatures. So these are here, but we need to select T in. We will say apply and close. Now we can run this simulation and we can get the results, but before that, just again let me tell you what I did. Okay, first let me remove this one so that it would be easier. These are some conditions that we have defined earlier. Okay, let me bring this one also down because this one is just the mathematical equation to tell you. These are three main expressions that need to understand. So we have used this one as our condition into our boundary condition T in, and T in, it is saying this condition and it need T conditional. So for T conditional it will check this equation. This equation is equivalent to T conditional, and in T conditional there is another variable that is inlet temperature. For inlet temperature it will come over here. We can bring everything into that one. For example, for instead of T conditional we can directly write this expression, so that would be true. So we can do like that, double if statement. And over here we can do another one, but that will become too complicated. So we can do like that, or we can reduce our expression to two expression, but I prefer do it in stepwise so that if there is any mistake, so it is easier to find out that mistake. So now we have defined all of our these parameters, and now we can run this simulation and then we can check our results. So I will run my previous simulation because it will converge faster. So let me say calculate. I did not initialize because I was running this simulation and it has already been initialized. So it will start from the previous results. I have plotted some results that you would be able to see just in a minute. Yes, here simulation is running and you can see some results. I have plotted the inlet temperature and outlet temperature. So a few things about these things. So first you can see this outlet temperature, it is coming from way below. It is because the outlet temperature at the first iteration it takes at 0 Kelvin. So because at very first iteration there was no temperature, so that's why it is starting from minus 273 degrees Celsius or 0 Kelvin. So that's why it is coming from below. And then the outlet temperature it is increasing over here, and you can see inlet temperature it was constant for some time. then after this time it is started increasing. So it means till this point the cooling power was enough, so whatever the outlet temperature, it was able to cool down to till 20 degrees Celsius. After this one the outlet temperature is higher, so it can cool down only up to this much, and the inlet temperature is increasing based on the outlet temperature. So this simulation is more realistic, and it takes into account the circulation of the cooling fluid. So that's how you can use expression in your simulation. So you can really use for complex situation, and of course it depends what kind of problem you have, but you can really solve a lot of problem without going into the UDF. So you don't need programming, so just with simple mathematical expression you can solve most of your problem. Okay, I will stop here and I will just show you the results. So simulation is not finished yet, but I can show you how it will look like at this stage. So stop at the end of timestamp, and we can go to graphics, contour, and we can see the temperature plot for everything. That's how our fluid look like. It is over here, it is at 25 degrees Celsius right now, so you can see the inlet temperature, it is approximately 25 degrees Celsius, and it is changing towards the outlet. And you can see they have a different temperature profile. It is because of different thermal conductivity I have defined here. The thermal conductivity is different for this cell, and I have defined in the different way for this cell, but that's not important at this stage, only to see that simulation is running and we are getting some results. And that's it for this expression. So we have really started from very simple expression and we move to the complexer one. So I hope you found all these examples useful, and you can utilize these videos for, or these expression for your simulation case. If you like this content, please like and subscribe to my channel. Thank you for watching, and see you in the next video.